Hello, everyone. I just wanted to talk about the mass measurement in the first experiment because I feel like a lot of people are still pretty confused, even though they did it, of how the error propagation works and why they're doing it, and even why, when you put multiple masses on a scale, does that give you some advantage, right? Like, we found that when you put multiple masses on the scale, the error propagation tells you that, oh, well, to find the value of one mass, you can divide all those masses and you can divide the uncertainty by that same number. But like, why does that advantage come up? And I just want to link it to that the dosing example, where you underdosed your patient because you weren't measuring it properly. So let's say I have some mass measurement, and I went through this with a few people, but I want to make sure everyone has it. So let's say you have some mass measurement, and I've measured one mass, and I get a value of 3.0 grams on my scale, right? Well, what does that mean? That means that my scale, because it has one increment, it means that this number can be as low. Like, there's some real mass, right down to the atom, that this thing has that I'm trying to measure. But this scale isn't giving me the real mass. This scale is telling me that, well, the mass can be as low as 2.95 grams, because if it were any lower than that, it would round down and read 2.9, right? So it has to be higher than that because it rounds up and reads 3.0. Okay. Or it can be as high as 3.04 repeating nines, right? Any number lower than that rounds down to 3.0, okay, in the scale. So the way we represent that is with this uncertainty in the increment. I'm going to call it 0.05 grams, right? It's plus 5 going in the top direction. That's as big as the mass could be, and minus 0.05 in the lower direction. Okay. But let's just for a second, let's imagine that the mass actual, imagine we actually knew it. Imagine it was 3.039 going on, right? And it has a bunch of decimal places. Well, if I took one of these masses and added them up over and over again, I would see, like, let's say I had like 5 of them, and I did the mass measurements one at a time. Well, I'd measure 3, and I'd measure 3 again, and I'd measure 3 again, and I would never realize that this value here was actually a little higher than 3.0. But let's just put 2 of them now on. So let's say I have 2 of them, mass 1 plus mass 2. Well, if I add 2 of these together, what does this give? Well, this gives like 2 of them, so 2 times mass actual is equal to 6.078, right? That's right, plus some stuff, grams. Well, on my scale, I read now 6.1 grams, right? So 6.1, you'll notice, is not 3.0 times 2, right? So by putting the masses together, by putting 2 of them together, my decimal place can now start to realize that this decimal place is not 0, right? So I start to get extra information about my masses by putting more of them on together. And what does error propagation tell you? Error propagation tells you that, oh, well, if I want to find the mass average of 1, well, that's equal to, so I want to find the average of one of these masses. Well, it's 6.1 grams divided by 2, right? Which is 3.05 grams. So already my value is closer to the real value, right? And what is my uncertainty? Well, my uncertainty, I can just take this number. What we learned from error propagation is we can take this number and divide it by 2, right? 0.05 grams divided by 2 is equal to 0.025 grams. Maybe I should just go through this. Just one of the things that came up from the propagation of error, and just to be clear, is from the formula sheet, we found that we had this formula Z is equal to A over C times B, right? And this has some constant in the bottom. Well, if we just have one measurement, so this is if we have two measurements, it's if we have an A and a B, right? But we don't have a measurement B. So we just set this value to 1. And in the formula, we can also set the uncertainty of B equal to 0, because we don't have an uncertainty associated with a value we didn't measure, right? Okay. So we just get, this is our uncertainty. And let's make some connections here. So Z is my mass average. A is M1 plus M2, right? And C is this constant here, 2, right? Because that's my formula that I'm using to take the average. My uncertainty in Z, one of the consequences, if you're just dividing a function or multiplying a function by a number, the consequence is that the consequence of the formula is that the relative uncertainties of these two things are the same. And this implies that my uncertainty in Z is equal to Z times delta A over A, which is equal to because I know Z is equal to A over C times delta A over A is equal to uncertainty of A over C, right? So let's link these here. So delta Z is equal to this delta M average, that should be. The uncertainty in my original measurement is this one, and my constant is 2, right? So that's how that all works. Okay, but I wanna go a little further. Let's copy some of these values and show this really at work. I'm gonna add a couple more decimal places to make this just a little more accurate. 362. Okay. But it keeps going, right? There's some very exact value this is. Okay, what happens if I do this with 10 masses? Okay, so with 10 masses, what is this actual mass? So this times 10 is equal to 30.39362. Okay. Right? Well, what does this read on a scale? Well, if I put this on my scale, M of, I'm going to just call this all 10 masses, would read on the scale 30.4 grams, right? That's what that number would read on the scale, right? This would round up to, okay. And this single measurement has the same uncertainty as this, right? Okay. Now, let's find the mass of one coin, the average. Sorry, I take this number and divide it by 10. I get 30.4 divided by 10 grams, 3.04 grams. Let's do this right. 3.04 grams. Well, that's actually really close. Getting closer to the actual real mass of this thing, right? Okay. And what's my uncertainty in this average? Well, I take this and divide it by 10, and I say my uncertainty is 0.005 grams now. And so now my value is 3.040 plus or minus 0.0050. This 0 appears because when I do this division, right, this is actually zeros all the way. Like I'm dividing by an integer. So this is 0.00000, right? When I do that division. Whoops. So this is my value. And what does my uncertainty say? Well, my uncertainty says that my mass, the lowest it could possibly be, is this value, right? And the highest it could possibly be is this value, right? Well, and it turns out that if I look at my next decimal place, like that does fall in here, right? So we see that by putting extra masses on the scale, and by using the fact that when I add 10 of them, I have the same uncertainty, so my relative uncertainty is now lower, I get this advantage where I can slowly converge on what the mass of one coin is. Okay, so hopefully that brings some stuff to light for the lab. At least in terms of how error propagation and the masses work.